Hind everyone. My name is B.N. Pandey and I am working as Assistant Professor in Ajay Kumar Garg Engineering College in Department of CSC. In previous lecture, I have talked about Compiler Design Unit 2 for description or introduction about parsing technique. Now I am talking about the one of the particular part that is basically called top-down parsing. We have two approaches for parsing. One is top-down parsing, that is started with the leaf, started with the root node. Means you have to start with the grammar terminal start symbol and then you have to expand up to a particular string which is accepted by that grammar. That is called top-down parsing, and bottom-up parsing is basically started with the leaf and expand up to the start symbol. So in top-down parsing, when we are starting the parsing approach with a start symbol, some of the problems will be arised during this top-down parsing. So we are going to discuss all these things in this lecture. So I'm going to cover what is top-down parser. The basic parsing technique that is associated with the top-down parsing is predictive parser, and it has two particular segments, which is backtracking and non-backtracking predictive parser. And LL1 parser is a kind of predictive parser which is basically applying this top-down approach, and it is called LL1 parser because the first L stands for left to right. The first L stands for left to right because the scanning process is left to right, and the second one is uses leftmost derivation. So that is called LL1 parser, and 1 stands for look ahead. So that is the total meaning of this LL1 parser. So if you are talking about the top-down parsing, the parse tree is created top to bottom. If you are taking this grammar, A produces BC, then B produces A, C produces C. So if you are talking about this grammar, the particular starting point is this start symbol, and then we have to approach the particular string which is accepted by that grammar. So this is called the top-down parser. If you are talking about top-down parser, the general type of parser is called recursive decision parser, and it contains both the approach in which backtracking is needed. It is a general parsing technique but not widely used, not efficient. Why it is not efficient? Because backtracking is applied in that when you are taking complex grammar for parsing this, by using this for parsing that grammar by using this recursive descent parsing. What is the problem with that? If you are using the backtracking, a lot of program would be right to remove this backtracking, and which is specific for that grammar, specifically that grammar. Okay, that why it is not very general parsing technique, it is not very efficient. But if you are talking about predictive parsing, it has no backtracking. Means whatever procedure you have applied, initially you have to give the input and finding the output. If in between any particular problem is there, definitely this parser will fail to generate the parsing tree for that grammar. So it is very efficient because it does not contain backtracking, it does not contain left recursive, because this kind of problem is associated with the top-down parsing. We will discuss later, and I have already discussed this left recursion and backtracking in previous lectures. Then it is very efficient parser. Why it is efficient? Because it parses number of grammars except ambiguous grammar and some of the grammar which have some anomalies. Needs a special form of grammar. So whatever grammar that is parsed through predictive parsing is called LL1 grammar. So all particular grammar which is passed through this particular predictive parsing is called LL1 grammar. So whatever grammar is passed through this predictive parsing is called LL1 grammar. So LL1 grammar are those grammars which is passed through this predictive parsing. Then recursive predictive parsing is a special form of recursive descent parsing without backtracking. So without backtracking means there is no backtracking. You are talking about recursive descent parser. We have already talked about recursive descent parser in this. If we needed that there would be some backtracking is there and we want to pass the tree, we are using this recursive descent parsing. Otherwise, we will use this recursive, this particular predictive parsing. It is a kind of predictive parsing which has no backtracking. So this is the strong feature of that. Okay. So if you are talking about recursive descent parsing, generally uses backtracking. What is the problem with that? if there is a backtrack is required, like this particular production you will see, BC by B. What is the problem arise when the particular current input symbol is B and the current non-terminal is capital B and current input symbol is capital B. Where the machine goes, either it goes with this BC or this B. That is the problem with recursive descent parsing. So it is some kind of manual process, means you cannot say it is completely automated process. Why you cannot say? Because when you are getting such kind of thing, and might be you will be started with this BC, and at the moment you will get that there is no solution area where do not get the solution of this problem. So what you are doing, you have to backtrack till that place and you have to again start with B produces B, and this B will provide you the solution. So it is some kind of manual process. It is partially manual, it is partially automated, it is not completely automated. That's why it is out of use, it is less efficient, and there is no much use of this particular parsing technique because it is no automated parsing technique. So this is the problem with this recursive descent parsing, uses backtracking. Now if you are talking about predictive parser, the predictive parser, firstly what you have to do, we have already discussed, eliminate left recursion, eliminate left factoring. Eliminate left factoring means eliminate backtracking and make the grammar as a left factored. So these are two kind of problems which is arised, and if any grammar having these two problems, one is left recursion and second one is backtracking, firstly you have to eliminate these two problems from the given grammar. After that it is suitable for predictive parser. So that is written over here, a grammar suitable for predictive parsing, a LL1 grammar. Which one is LL1 grammar? That is not, we are saying that because LL1 grammar is that grammar which is correctly passed by the predictive parser. But initially, which grammar is selected for the predictive parsing? Okay, that is very important. So you have to select that grammar in which there is no left recursion and there is no backtracking problem and the grammar is left factored. So this is primary concern. Whenever you are going to solve any problem using this predictive parser which has no backtracking, firstly you have to make that grammar suitable, eliminate left recursion, eliminate backtracking if it is available or it is available with that grammar, associated with that grammar. So this is the important step. Whenever you are going to use any grammar for predictive parser, firstly you have to check for that either it has some left recursion problem or backtracking problem. If it is there, firstly you have to eliminate, then only you can put up that grammar as an input for predictive parser. For that, two steps are used. Eliminating left recursion, I have already discussed in last lecture. Eliminating left recursion and eliminating backtracking. Then only this grammar is suitable for predictive parser. Okay. Like this is the example, dangling FL's example, and you better know this is basically this particular grammar is basically ambiguous grammar, and there is no parsing technique which is alone sufficient to parse this ambiguous grammar. For parsing ambiguous grammar, we have to use this operator precedence parser, so that whenever we are getting some conflict at that moment, we have to finding out the operator precedence in between two particular conflicting productions where some particular terminal is involved. We have to identify that terminal, then finding out the precedence in between that, resolve that conflict, and then we will make a parsing table which is actually correct parsing table for ambiguous grammar. So predictive parser is inefficient, unable to parse the ambiguous grammar. So when we trying to write the non-terminal statement, if the current token is if, we have to choose first production rule. First production is, there are two methods are used for finding out first and follow for developing this predictive parsing table. So for finding first, we have to use this. When we are trying to write the non-terminal statement, we can uniquely choose the production rule by just looking the current token. We eliminate the left recursion in the grammar and the left factor it, but it may not be suitable for predictive parsing. This particular grammar is specifically not suitable because it already has ambiguity and it is ambiguous grammar. That's why it is not suitable. Even you are just eliminating the left factoring, still there is a problem when you are completely execute this predictive parsing with this grammar. Now we are talking about non-recursive predictive parsing. So non-recursive predictive parsing is a table-driven parser. So what is the process of this? This is the model for that. You can see that this model. Okay. There is a stack. So if you are seeing the content of a stack will contain the particular grammar symbol followed by $. There is input buffer. It will contain all the input alphabet A1, A2 up to AN. Then there is a predictive parser procedure in which what we are doing, we have to generate a parsing table and there is a program routine that is called predictive parser. This program routine will provide the combination of a stack and this input symbol, and that will derive the parsing table. Means it will take the value from the parsing table, depends upon the situation of a stack and situation of input symbol, and accordingly there is a program written over there through which you can identify that what particular action should take. So this is the basically non-recursive predictive parsing, that is called LL1 parser, and that is basically elimination after elimination of backtracking and after elimination of left recursion. You can use this particular grammar for this parsing technique. Although it is not confirmed that this particular parser will parse that grammar. If the parser is correctly passed through this grammar, this particular parsing technique, if the grammar will be passed through this parsing technique, then it is only called the LL1 parser. So LL1 parser is that where predictive parser is correctly and efficiently applied to the particular grammar. Then only it is called LL1 grammar and the particular parsing technique is called LL1 parser. Now what are the constituents? Input buffer, whatever string you want to be passed, that particular string will be taken as input buffer. Then what is output? Output is what if that string is correctly passed and we are reaching at the halting state, there will be some indication for that. If you are reaching on that state, definitely we are getting this output for that. And output is what we can design the parse tree for that. That is the basic output. Then a stack contains the grammar symbol, and the bottom of the stack we are using some right hand marker, bottom end marker, because marker is the indication of completion of the particular sequence. If you are using some, so there should be some indication where we can just say that the particular process is ended. So for that purpose we are using this bottom end marker, and right hand marker we can say that according their position. Initially the stack contains only the symbol $, and the starting symbol S. So we have to start with that. $S is the state of stack, and input, some input is there, A1 plus A2, whatever input is there here. So the triggering is there if you are taking this start symbol as capital S and then small terminal. We are just generating a parsing table. In that corresponding entry will be, it is a two-dimensional table where the particular rows are consisting of constituting with basically start input alpha variables, and all the particular columns are having values of terminals. So at the moment, if you are seeing that capital S is on the row and small a as the column, that particular block contains some value. Through that value we can assess the process. And what is the indication of completion of this? When the stack is empty, if only $, is left in the stack, the parsing is completed. Means all the particular input is exhausted and the input is already processed. At that time we can say that, and the stack is going to be empty. At that time we can say that the process is completed. Now what is parsing table? Parsing table is a two-dimensional array that would contain start the variable as a row and terminal as a column. So this is the constitution of parsing table, and the complete process of LL1 parser is to derive that parsing table. So what we are going to study here, to derive that parsing table from the given grammar. That is our purpose, to derive this parsing table. Each row is a non-terminal symbol, each column is a terminal symbol, or the special symbol dollar. Dollar is also counted as a terminal. Each entry holds a production rule. So whatever corresponding entry is there, by deriving this parsing table, we are getting some production into that. So whatever entry is there, we are having some production. How we can use this production, we will just discuss in this lecture. What are the actions involved when we are getting a situation where some, like if stack contains, suppose, $S and input contains A plus B and dollar. Now you can see that S is the top of the stack, as small a is the current input symbol. So there is a table, here S, and here some production. S produces A, suppose. So what we are doing, there are three situations are there. Okay. So the symbol at the top of a stack and the current input symbol, current symbol in the input string say A determine the parsing action. So I have already told you, okay, this top of a stack and current input symbol will say, and we have derived this table before, so that we will refer the value of the corresponding entry and accordingly we can act that. So there are four possible parser actions. The first, if X and capital A are dollar, so maybe here is also dollar, here is also dollar. Okay. At that case, parser halts, means it will show that all the inputs are exhausted and this particular start symbol is also exhausted. So you have processed successfully all the particular non-terminal contents and terminal contents, mean all the terminals are exhausted. So that is the successful condition. Means when you are going to perform this stack implementation and you are getting this situation, at that moment you will say that the successfully completion of the stack, the particular parsing technique. Now, if X and small a are the same terminal symbol, different from dollar. So suppose now dollar small a is there and small a is there. What we are doing? We have to pop this from stack and remove it from current input symbol. So whenever both are same, what we are doing, we have to pop this from that. So dollar is at the particular point and small a is removed from the current input symbol. Third situation is there if X is a non-terminal like capital S and current input symbol is small a. Then what we have to do? We have just finding out the particular entry corresponding M table S comma A. Like here S produces small a. What we have to do? We are just placing this S from this small a capital A by reverse order. Whatever order you are just reading it from left to right, you have to place it on that order in the stack. Small a is read first, so it is entered last. Okay. Capital A is read last, so it is entered at last. So top of a stack would be small a, then capital A, means in the reverse order in the stack that will be located. Okay. So that would be there. So what do you have to do? You have to do this. If it is non-terminal. None of the above is there. If there is no any combination, suppose capital S is there, small a is there, and S and capital A are empty. Like suppose I have taken dollar A, capital A, and here small a. Here we are putting capital A and small a, and there is no entry. So all blank entries are treated as error. So these entries are error. So four types of situation. If both are dollar at the stack and at the input symbol, then it is halts. If both are input terminal, same input terminal at the stack and at the input symbol, we have to pop up this input symbol. If there is a non-terminal at a stack and terminal at a particular input symbol, what we have to do? We have to refer this parsing table and we have to get it out which production is associated with both the corresponding entry. We have to reversely place it into the stack. Okay. Then if there is a blank, there is an error. So these 4 type of actions are generated when we are getting such kind of situation. So this is the example. So you have to see this grammar. S produces ABA, B produces BB by epsilon. Firstly, we have to check for the left recursion and backtracking. So you will see that there is no backtracking and there is no left recursion. And important part, it is applied on the context-free grammar. So every particular production in the form of A produces alpha, where alpha belongs to V union T closure. So you will see that every grammar, each and every production is in this form. It is context-free grammar. Now, this is the table for that. S produces ABA, B produces epsilon, B produces BB. Now, if you are going to derive this string, this is the input. Initially, the stack contained $ and S. This is the output, which particular production is used for that. Now, S and A. So, you will check this entry. S produces ABA. So, what is the situation? S will be replaced by A capital B A. And here input is A B B A $. Now you will check the current condition. Small a, both are same input terminal. So you will remove that. Then again the situation is $AB, BB A $. Now B and B you have to check. B and B, BB. $A. B is replaced by capital B and B. Here BB A $. And you have to use this production also here. B produces BB. Here S produces ABA. So write like that. Finally this B and B. Again $A B B, because B and B is there. ABB. Then B A $. So here we are using B produces BB. Now again B and B removed. The situation is capital AB A $. Now B and A, that is B produces epsilon. A, B is removed because B produces epsilon. If you are putting, B is removed. A and A $. Now A and A exhausted and $. So this is the successful completion of this particular grammar, given grammar, and this shows that this grammar is LL1 grammar and successfully passed using this LL1 parser. So this is the correct grammar. Okay, so this is the process and you are using these grammars. So if you are just tracking out, you will get S produces ABA, then A, BBA, because B is derived by BB, then again A, BB, BA, okay, then again this B is derived by epsilon, A, B, B, A. So now you have to reach this. So in left derivation, every time we are using this left derivation, by using this left derivation, it is derived that. So this is the basic. But how we can find this parsing table? That is very important part. And basically the whole mathematical formulation will be used to derive this table because it is very easy process. It's not very tough. But actual implementation is that. But how we can derive this table from the given grammar, that is very important agenda. And now I am going to discuss this agenda. Okay. I have already shown you that this is leftmost derivation is used. This is second one example and this is given. Now how we can construct this LL1 parsing table? So when we are going to construct LL1 parsing table, we are using two algorithms, first and follow. And then applying this first and follow. After that, there is a algorithm for constructing LL1 parsing table. So this particular process is given, constructing LL1 parsing table. So firstly, we have to derive this first, then derive this follow, and then we are using this first and follow to derive this parsing table. So two functions are used. First is what? Whatever first terminal you are scanned from left to right, in the right hand side of the production, that is called basically first, and it constitutes three rules. We will discuss in next particular, this is the construction for first. So what is capital X? Firstly, notations. It is very important to understand the notations used for deriving this first and follow. We are using capital ABC for non-terminal. We are using small ABC plus minus for terminal. We are using X, Y, Z, capital R for grammar symbol. And we are using alpha, beta, gamma for V union T closure. And you will see that these four symbols are used to derive this function. So first rule is what? If X is a terminal symbol, because capital X is a grammar symbol, it might be non-terminal or terminal. So if capital X is a terminal symbol, then first of X is X. Simple. Means every terminal is first of itself. You can anywhere use any terminal as a first. Second, if X is a non-terminal and X produces epsilon is there, if any particular variable directly derived epsilon, then epsilon will be added in the first of X. Okay. If X is a non-terminal symbol, one important rule is missing. If X produces small a alpha, that is rule. If X produces small a alpha, then small a is also comes in first. And the third rule is very important. If X produces Y1, Y2 and these all are basically non-terminals, and if Y1 derives epsilon, then whatever Y1 contains except epsilon is the first of X, except epsilon. Epsilon will not be added. And also Y2's first is there. If Y2 is also epsilon derived, then Y2's first is there except non-epsilon. All non-epsilon symbol will be in the first of X, and it is going on. If this complete will derive epsilon, means Y1 up to Yk all derives epsilon, then only this will be derive epsilon. So this is the rule for first. Today I am just completing this lecture this time. Next time I will be given some example for first, and then we are going to calculate the follow of the grammar. Thank you very much.